Welcome back to the course of chemical crystallography. This is the beginning of 4th week. So in the previous 3 weeks we have learned some of the basic aspects of crystallographic symmetry, point group, space group. Then we understood the aspects of planar density, linear density, and from there we calculated the atomic packing factors and all that. So today we will start the theory of X-ray diffraction, and we would like to introduce you to the Bragg's law and then the concept of reciprocal lattice. As we are intended, we are interested to learn the X-ray crystallography using X-ray radiation, and all of us are aware about this spectrum of electromagnetic radiation in terms of wavelengths. Once again, to remind you that the X-rays fall in the region of 10 to the power minus 10, about that kind of wavelength, 10 to the power minus 10 meter. So the wavelength is extremely small and highly penetrating in nature. So we use X-ray radiation to identify the crystal structures. The theory of diffraction goes like this: when a set of parallel beam of X-rays fall on a scattering substance like a crystal, two things can happen. A set of parallel beams can get scattered or diffracted from the source of scattering, which is a crystal. So the source of scattering can do two things. One is that the waves that are falling on the scattering substance, the wave 1 and wave 2, they can be diffracted having the same phase as that of the incident radiation. So when such scattering happens, the scattered radiation is enhanced in their intensity. That means the amplitude of that scattered radiation is twice the amplitude of the incident radiation, and what we see is a diffraction that takes place. On the other hand, when two waves, suppose wave 3 and wave 4, undergoes a scattering event through a crystal and they come out as offset, that means they are not like before and they don't combine together to give a diffraction data, what we get is something like that, which means there is no diffraction, the interference is out of phase, and hence we don't see any diffracted beam. So this phenomena was observed by Bragg in 1912 to 1914, immediately following the discovery of scattering of X-rays by Max von Laue in 1912. So the father and son Bragg's, they introduced the world famous Bragg's law in X-ray diffraction. So how they interpreted this diffraction is very important. So here, if we have two sets of crystallographic planes A and B containing a set of scatterers, those are scattering centers, maybe atoms, and when that particular set of parallel planes, which are planes of A and B, at a distance dHkl, which we have identified on the right hand side, that these two planes are facing the incident beam as we are indicating here. So a set of parallel beams 1 and 2 of a particular wavelength lambda is falling on a crystal. What can happen is they can get diffracted in the direction of 1' and 2'. So the angle of incidence is theta and angle of diffraction is also theta here. So now these two waves 1 and 2 are getting diffracted from two parallel layers of scattering centers and going back to the viewer. So what Bragg and Bragg proposed that the path difference of these two waves, that is the wave number 1 and wave number 2, if it is integral multiple of the wavelength, then the scattering is in phase, a coherent scattering, and as a result a diffraction is observed. So by doing a simple geometric calculation, we try to understand how the Bragg's law can be derived. So here the point P and Q from where the diffraction takes place. So the beam 1 gets diffracted from point P and beam 2 gets diffracted from point Q. So now if we drop a perpendicular from P to the line number 2 and from P to the line number 2 prime as S and T, which means that the portion before diffraction up to P is same as up to S in case of 2. After diffraction, P2 to 1 prime and T to 2 prime is again same. So the path difference between the diffracted beams 1 and 2 is nothing but SQ plus QT. And what Bragg proposed is that this path difference SQ plus QT should be integral multiple of the wavelength to observe any X-ray diffraction from a set of planes kept at dHKL distance. So now if we want to see what is SQ, we look at SQ, and very simple geometric understanding can indicate that the theta here is same as the theta here in the triangle SPQ, and similarly PQT. So now as we know, PQ is equal to dHKL, the distance between a set of HKL planes. So n lambda is equal to SQ, which is d sin theta, that d sin theta, and QT is also, this QT is also dHKL sin theta, which means n lambda equal to 2 dHKL sin theta. And this is the famous Bragg's law, and it is so simple but so important in X-ray diffraction. So about 100 years ago this particular law was proposed by Bragg, and it opened up a new area of X-ray crystallography since then. So at this point I would like to draw your attention to the geometry of a powdered X-ray diffractometer. The geometry is like a circle. This circle is called the circle of diffraction, where we have a source of X-ray at the point T. So this can be any kind of X-ray source like the seal tube X-ray or microfocus or whatever we have understood, we have learned before. And then we have a sample at S, which is the center of this circle, and the detector C is kept on the circumference of this particular circle, and the O is the axis for rotating the detector and the sample. So now when the beam falls on the sample S at an angle theta, we measure the diffraction from that sample at an angle of 2 theta. And then the diffraction is recorded and represented. Here I would like to show you one very ancient days powder X-ray diffraction recorded on a photographic film. So what we see here is at the center, the dark spot indicates that there is a beam stop somewhere here, which stops the beam from falling on the X-ray plate. So the beam stop can be here, it can be placed very close to the sample as well, depending on the geometry of the diffractometer. And then when the diffraction happens from the powdered sample, it happens in a conical manner. So if you have a sample here, the cone behind this is the angle of diffraction, and then if you place a photographic film behind it, what you would see as the concentric circles of bright lines. Those concentric circles of bright lines indicate that the diffraction is happening at different angles for the particular set of crystal. In case of powder diffraction, as we know, it is a collection of large number of microcrystallites and they are all oriented in all kinds of different directions. So what we get to see is a two-dimensional pattern of intensity versus 2 theta using a modern day's diffractometer. This is a data recorded using a scintillation counter detector, which is a point detector and it detects only 2 theta of a particular width at a given point of time. So when we record this X-ray diffraction data, we get to see a set of peaks. These peaks indicate that those particular d values at which the Bragg's law is met, we see a diffraction, and wherever we don't see any peak means there is no constructive interference of those X-ray beams. Using this very simple technique of powder X-ray diffraction, one can identify the type of lattice that one is examining in a given sample if it is a cubic system. For monoclinic or triclinic or any other symmetry, things are slightly difficult, but for simple system like cubic system, powder diffraction data can be used very easily to identify the lattice centering. So what we do is we record a powder X-ray diffraction data from about 3 to 50 to 100 degree in 2 theta, and then we find out the 2 theta positions where all we get peaks, and then we try to calculate the sine square theta value for each of those peaks, and we apply the Bragg's law in a slightly different manner, where it is sine square theta equal to lambda square h square plus k square plus l square by 4a0 square, and we use the simple equation dhkl equal to a by square root of h square plus k square plus l square for cubic systems to calculate the lattice parameter A. Let us see with one example how to find out the HKL indices and crystal structure of a cubic system from powder X-ray diffraction data. So to start with, what we have is a set of peaks and the corresponding 2 theta values as listed in column 1 and 2. So now we calculate the corresponding sine square theta values for each of those peaks and write it down. Now we try to find out a common factor in this column of sine square theta, where if we divide all these numbers by that common factor, we should end up getting integers. So in this particular case, what we find is the first term 0.308 serves the purpose of a common factor. So that common factor is used to divide all the values of sine square theta on this column and is written in the fourth column. So now these are integers, and as we have seen in the previous slide, where sine square theta is proportional to h square plus k square plus l square with a constant lambda square by 4a0 square, we multiply this fraction by 2, a constant quantity, and get the set of integers like this. So now this h square plus k square plus l square corresponds to 2, 4, 6, 8, 10, 12, 14 and 16. Why did we do that? Because we see that if h square plus k square plus l square is 1, we are not able to write unique values for H, K and L for all these numbers. Why are we multiplying it by 2? Because when we try to understand if the H square plus K square plus L square is equal to 1, what are the possible values of H, K and L? It can be 1, 0, 0, 0, 1, 0, 0, 0, 1. When it is 2, it can be 1, 1, 0, 0, 1, 0, 1, 0, 1, 1. In case of 3, it can be 1, 1 and 1. In case of 4, it can be 2, 0, 0, 0, 2, 0, 2 and 0, 0, 2. In case of 5, it can be 2, 2, 1, that is 2 square plus 2, it can be 2, 0, 1, so 2 square is 4 plus 1, 5. In case of 6, it can be 2, 1, 1, which means 2 square plus 1 is 6. But now for 7, we are stuck. 7 cannot be represented as squares of 3 integers. And then we first multiply it by 2 and see if all the numbers that we generate on the column 4, whether it can be written as a combination of 3 sets of integers. So now when we have multiplied by 2, we have the numbers 2, 4, 6, 8, 10, 12, 14 and 16. So now 2 can be written as 1, 1, 0. Actually, it can be 0, 1, 1 or it can be 1, 0, 1. 2, 0, 0, which means it can be family of planes of 2, 0, 0. 6 is 2, 1, 1. So it can be family of 2, 1, 1 planes. 8 can be written as 2, 2, 0, that is family of 2, 2, 0. 3, 1, 0 and so on. So what we can see here is that only a set of HKL planes are allowed in this particular diffraction pattern, not all possible values of HKL. For the time being, make a note that for simple crystal, if it is a simple cubic system, the combination of H, K and L, the H square plus K square plus L square, should be equal to 1, 2, 3, 4, 5, 6, 8, 9 and so on. For body-centered cubic lattice, it has to be 2, 4, 6, 8, 10, 12, 14 and 16, which is the case here. And in case of face-centered cubic, it has to be 3, 4, 8, 12, 8, 11, 12 and 16. So by looking at the fifth column and comparing it with the value for body-centered cubic, we conclude that this is a body-centered cubic lattice. And then if we try to calculate the lattice centering lattice parameters, we take one of these 2 theta values. Suppose we take the last one, 2 theta for 400 reflection as our standard reflection. So theta is 29.71. So we calculate the D400 as equal to lambda by 2 sine theta, because we are applying Bragg's law. So we calculate the D400 to be this number 0.71699 angstrom, and then from that we calculate A0 equal to D into square root of H square plus K square plus L square. So we multiply D with square root of H square plus K square plus L square, which is 4, because here HKL is 400, so 400 square is 16 and square root of that is 4. So A0 can be calculated as 2.868 angstrom. So this is how one can calculate the lattice parameter and identify the lattice centering of simple cubic systems. It can be simple cubic, body-centered cubic or face-centered cubic. One can determine the lattice centering correctly. Now let us try to understand how this Bragg's law can be applied to understand the choice of radiation. As we know, we write Bragg's law as n lambda equal to 2d hkl sin theta, and we generally construct n equal to we write n equal to 1. So the maximum value for maximum value of sin theta can be 1, which indicates theta max can be 90 degree. So lambda equal to 2d hkl max is for theta equal to 90 degree. So dhkl max is equal to lambda by 2. So now if the wavelength is copper K alpha, my lambda is about 1.54 angstroms by 2, which is equal to 0.77 angstroms for copper K alpha radiation, and the same is equal to 0.71 by 2 as 0.35 angstrom for MO K alpha radiation. Mind you, these are very approximate values. I have not taken values up to 4 decimal places, which indicates that using molybdenum K alpha radiation, one can go to a very high resolution of 0.35 angstrom in D values and get the information on that particular crystal structure to a very high resolution, whereas using copper K alpha you can only achieve a resolution of 0.77 angstrom. Now I would like to introduce you to the IUCR limits. What is IUCR? IUCR is the short form of International Union of Crystallography, and it is a big association of crystallographers across the world, and there it is recognized that for molybdenum radiation, one has to achieve a data up to 50 degree into theta for an acceptable crystal structure solution. So what does it mean? A 50 degree to theta means 25 degree in theta. So for molybdenum radiation, which is about 0.71 angstrom, is equal to 2d hkl sin 25 degree, which means dhkl can be calculated as 1.183 angstroms. So we write the resolution in terms of reciprocal distance, that is 1 by dhkl, as equal to 0.84 angstrom inverse. So this is the resolution that is minimum required for a publishable data in any crystallography journal. So if you do the calculation for the same using copper radiation, and if you want to achieve this resolution, what should be the 2 theta value for that particular case? So when you use copper K alpha radiation, you use wavelength of 1.54 angstroms, which is equal to 2 into the corresponding D should be about 1.2 angstrom, and I need to know the corresponding sin theta. So if you do this calculation, you will find that theta is about 42 degree, which means 2 theta is about 84 degree. So in case of copper, you need to collect data up to a very much higher angle compared to a molybdenum data to achieve the same resolution. So this indicates that by using copper data, you should collect data up to a high angle. If you are collecting using molybdenum, you restrict yourself up to 50 degrees of 2 theta to collect a routine X-ray diffraction data. So from here we will continue in the next lecture to discuss about the choice of appropriate radiation for macromolecular crystallography and small molecular crystallography, and we will see why do we need to use copper radiation for powder X-ray diffraction and why do we use molybdenum for single crystal X-ray diffraction. From there we will start discussing about the introduction of reciprocal lattice, and we will try to understand the theory of X-ray diffraction using reciprocal space.